Hey guys! Alright, so we just spent the last week looking at graphs of ellipses and writing equations of ellipses. And this last little bit of section 2 that we're going to look at is just look at some applications of this stuff. So specifically kind of writing equations of ellipses and how we can utilize them. And one of the most common places where we see ellipses is the idea of orbits. So the moon's orbit around the Earth follows the path of an ellipse. The Earth's orbits around the sun follows the path of an ellipse, so on and so forth. All the planets, their orbits are elliptical orbits. Now, one thing that you may not realize, and what is commonly mistaken, is the Earth is actually not the center of the moon's orbit. Likewise, the sun is not the center of the Earth's orbit or any of the other planets. What it actually is in terms of the moon's orbit, so that's what we're talking about in this problem, the Earth is actually on one of the focal points. So the Earth is located on one of the focal points of the moon's elliptical orbit. And so depending on where the moon is on its orbit, sometimes it's closer to the Earth, sometimes it's farther away from the Earth. And so what we actually can do is we can use this information to help us write the elliptical equation of the orbit. Okay, so we're writing an equation of an ellipse. So just like we were doing before when we were writing an equation of an ellipse, there's some things we want to look for. Now, so these are the big things you want to look for. That being said, when you're coming up with an equation for planetary orbits, lunar orbits, or really any kind of elliptical path in a in really any situation, generally what you're going to want to do is, unless for some other reason you have a specific reason why you would want to do it differently, usually what you would want to do is you want to just make the center be at 0, 0, and you can go ahead and make it horizontal. Okay. Generally we just make the center of whatever our orbit is at 0, 0, unless we're comparing it to other elliptical paths or anything like that. In that case, then we would want to come up with a more standardized grid system. Okay, so we're going to go ahead and we're going to say that we're going to make the horizontal axis be the major axis, and we're going to let our center be at 0, 0. And in this problem, I went ahead and actually told you that stuff, but even if it doesn't tell you that, you can go ahead and kind of do that yourself. So really what we need to figure out is we need to figure out the A and the B. But the only pieces of information we're given is that the closest the center of the Earth is to the moon is 363,292, and the farthest is 405,508. So here we have an elliptical path. The moon is on that major axis and it's at one of your focal points, the closest a focal point will ever be to the actual ellipse. So I know my picture might not be super easy to see because my picture's not a perfect an ellipse, and my point is not necessarily where the focal point would be, but the closest point on an ellipse to one of your focal points will always occur on the major axes. It'll be that vertex on that side. So what that tells us is that this distance right here is at 363,292. And then the farthest away it will ever be is to the other vertex. So 405,508. So this is what we know. Okay, so the closest point to any focal point is the near vertex, and the farthest a point can get from a focal point is the opposite vertex, the vertex on the opposite side of the ellipse. So with that together, what we can decide is that the major axes is equal to those two parts added up. So 405,508 plus 363,292. So the major axis is 768,800. Okay, and that's going to tell us, if you remember from writing our equations, if we know the length of the major axes, we can cut that in half, and that tells us that our A is 384,400. All right, now we need to find our B, okay? And what we can actually do, so the next thing that we can do, the other thing that we can do with this, with the information that we're given, is we can also find how long C is. Because here's our center, and we just decided from the center to that vertex was that length right there. That's what our A is. So that means that if I find the difference between these two numbers, my A and that shortest distance, that's going to tell me my C. That's going to tell me this distance right in here. So 384,400 minus 363,292 tells me that my C is 21,108. And if you remember from writing equations, if we know the A and the C, we can figure out what our B is. So 21,108 squared equals 384,400 squared minus B squared. And B squared is going to equal, let's see, 4,000 squared minus 21,108 squared equals 147,317. 123. That was 1.4 times 10 to the 11th. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And our b is going to be the square root of that number. So we get our b equaling 383,820. And so our equation is going to be x squared. I made my major axis the horizontal, so I'm going to put the a squared underneath that. So 384,400 squared. It's going to be a nice big number here. 14776,336. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Plus our b squared, y squared over our b squared, which was 147,317. 812,300, and then equals 1. All right, next